Okay, good. Welcome everyone to the latest seminar of the International Network on Quantum Annealing. I'm very pleased to invite our next seminar speaker, who is Koji Mizumatsu from Fixstars, and he's going to be talking to us about software architecture of Amplify STK/AE. So over to you, Dr. Mizumatsu.
Yes, thank you very much for introduction. So I'm Koji from Fixstars Corporation, and I'll be talking about the software architecture of Amplify software development kit and annealing engine. And I hope I get to clarify what I mean by that through this talk today. So let me, before going into detail, let me please go through some backgrounds. And first of all, I would like to introduce who we are, Fixstars. So we're a software company, and we're a group of experts with in software acceleration that maximizes computers' performance. And then we have a number of engineers with hardware expertise and capability to implement a fast algorithm, and also specialized domain knowledge. And then we make consultation using benchmark and identifying bottlenecks of customers' problems, and also do acceleration by improving and developing algorithms, and also optimizing hardware which customers are using, and so forth, and also support for integration into some products. And I put some example of what we work on. Here's the cancer image recognition based on AI. And also we work on acceleration of self-driving components. And as one of the things that we work on, we have this a system called Fixstars Amplify, which helps quantum based technologies, makes it easy to use. And then I hope I get to introduce this system today. Okay, so motivation for us to go into this quantum related technology was that the recent surge of quantum technologies, as I put this, I got this picture from some website showing like a number of companies nowadays working on some quantum technologies, ranging from very fundamental quantum mechanical researches to development of software regarding to quantum related technologies. And also I would like to note this quantum inspired, so-called quantum inspired Ising machines, also available from various companies, including ourselves, Fixstars, Fujitsu, Toshiba, Hitachi, as I listed over here. However, it's pretty nice that we are seeing all these quantum technologies, but it seems like a number of people who have access to these technologies are limited. It could be due to, it could be because maybe quantum mechanics is hard to understand, or also we think some of the technologies, the platform of the technologies have a lot of specifications. So one has to know a lot of these details to sort of start using these technologies. So that can be some obstacles. Hence, we developed this software called Amplify, Fixstars Amplify, which simplifies the access to some quantum technologies, and also hoping to help engineers to develop applications using these quantum technologies. So the target of this software is application development for combinatorial optimization problems. And the software has feature of hardware abstraction to access to various different Ising machines in a unified way. Also, to achieve that implementation of a lot of latest algorithms and knowledge done in this software. So this is a little cartoon of Fixstars Amplify, which I will explain in a later slide. But before going into detail, please let me acknowledge the government fundings. So some of the developments that we made for Fixstars Amplify were funded by these Japanese government's agencies, NEDO and SIP. So through these projects, we were able to collaborate with a number of universities and other companies, which gave us a lot of insights into developing this system. So I would like to acknowledge these fundings. Okay, so let me introduce the system. So it's a cloud service, and it's a cloud platform for DevOps for quantum computing, and specialized for solving combinatorial optimization problems efficiently on quantum computers, and also proprietary GPU annealing machines. And so we have this Amplify software development kits. Using this, you can create problem in simple way, and also allows us to connect to a number of different Ising machines. So from the quantum realm, we have D-Wave 2000Q Advantage and IBM Qiskit. That's a gate-based quantum computer, and also simulator. We get to connect those, and also a QLAX. It's a circuit simulator from Qunasys. And on the digital annealer side, we have Fixstars Amplify annealing engine, and also Fujitsu DA4, DA3, and DA2, and Toshiba SQBM Plus and SPM, and Hitachi CMOS annealing engine. And for software which solves optimization problem, it's a Groby optimizer. We also get to connect this software through Amplify SDK. So here are the features of Amplify SDK, and it's pretty simple. And you can just start by pip install Amplify, and you can just install it right away and start using it. And without knowing much details of the specifications of all these machines and the software, you can start using through Amplify. It's also pretty portable, supporting all these different machines. And so one of the machines that's supported is annealing engine that's developed by us, Fixstars Amplify annealing engine. So that comes with 260,000 bits, and it's a pretty big annealer, and that's also available through our system. So it's a free trial, although the timeout is limited, but you can start out free. And for certain evaluation and the verification purposes, it can be also free. And we have well-maintained tutorial and sample codes. So that can be also pretty helpful to start out using Fixstars Amplify. So you basically Google Fixstars Amplify, then you get a website, and you can go to our demo page, let's say. So we have prepared a number of demos, demonstration programs, and then you can go through all these programs to pick up the gist of Fixstars Amplify. So it's example of traveling salesman problem, and it's a rideshare problem here. And each one has a Jupyter notebook, and you can run it to see the details of how to use Fixstars Amplify. So this is the example of traveling salesman problem. So this Jupyter notebook goes through all the details, how to formulate problems of traveling salesman problem, and then actually using the Fixstars annealing engine to solve the problem, and then showing the results and so forth. So after you register, you can register and you can get the token right away, and you can just start using this kind of demos, and then you can start learning how to use Amplify right away. So if you are familiar with Python, the threshold is pretty low, I would say. And if you want to go into more details, we have pretty well maintained documents, pretty extensive. And if you want to go into some details and then do more things and so forth, then you can kind of dig into this documentation as well. Okay, so that's Fixstars Amplify SDK. And also annealing engine. So it's not quantum, but GPU accelerated ultra fast Cubo solver. So it's a pretty big annealer with 128,000 binary variables can be handled, which translates to 32 gigabytes of problem size. And it's operating on NVIDIA GPU V100 and A100. And also, when you try to solve this kind of annealing problem, you have to usually tune a lot of parameters. But Fixstars annealing engine does automatic tuning on various parameters. So as a user, you don't have to worry too much about parameter tuning. Okay, so it's a cloud-based. It's cloud-based, and you can use annealing engine via web API. Okay, so it's free for trial use and a pilot project use and academic research. So I hope you get some interest in using this system and then start using it with the free trial. And okay, why we want to use Amplify? So here we think that it's an ideal platform as a reference to facilitate POC and development of practical quantum-ready applications and hybrid quantum systems. So what I mean by that is the okay. So we already have some results using Amplify annealing engine. So I'll be introducing these things in detail later, but here's like calculation of a phase separation of polymer using Fixstars Amplify annealing engine. And so that's some academic result. And then the right picture, we use annealing engine, Fixstars annealing engine to solve assignment problem of the workers in warehouse. So we actually use annealing engine in this kind of company setting as well. So I will introduce those things in detail later. So we have pretty good motivation to start using or trying annealing engine. That's the point I wanted to make here. Okay, so Amplify SDK and annealing engine. So when you try to approach optimization problem, you have to construct a problem first. Let's say Cubo model and so forth. So that also takes some time to construct the problem. And the left figure shows the time it takes to construct traveling salesman problem with 10,000 variables. And the top two is our Amplify SDK. And so it shows that it's considerably faster than some of other systems that can also construct the model. Okay, so SDK provides a faster means to construct, formulate problem. And also regarding the annealing engine, so the right figure shows solving max cut problem with 2,000 variables. And the vertical is the energy and the horizontal is the sampling time. So the blue one is Amplify annealing engine, and the orange one is some other solver. So it shows that the Amplify reaches the energy minimum quicker than other solver in this instance. So it's a pretty quick annealer. So also has a pretty good motivation to use Amplify annealing engine in this aspect. So fast problem formulation through SDK and the fast annealing through Fixstars annealing engine. So that's sort of character of the system. Okay, so regarding the software architecture of Amplify SDK, so I put some example of how it goes about using Amplify SDK. So it's a Python written in Python code. It's pretty simple and intuitive. So I'm showing this example of solving Cubo in this particular case. So in order to approach this kind of setting, you first formulate problem. Okay, so in order to do so, you first prepare variables, can be scalar or multi-dimensional arrays of a binary 0, 1 variable or Ising variables like 1 or -1. And then using those variables, you construct objective function, which is to be minimized in an optimization problem. And then also problem might require some constraint conditions. So we might have to prepare constraint conditions. So in this particular example on the left, first you prepare some binary variables on the top part, and then you construct objective function using the variable that you prepared. So in this particular case, it's a pretty simple objective function, 1 minus Q0 times Q1. And just for the sake of demonstration, put in one hot constraint. So we have two variables here. So addition of two variables equals to 1. That's one hot constraint in this particular case. So after preparing objective function and constraint condition, you create a binary quadratic model, which is a cube, unconstrained binary optimization. So it needs to be unconstrained, but we have constraint condition. But this binary quadratic model converts constraint condition into quadratic model and so forth. So in the end, you end up having quadratic model here. And after having the model, okay, so at this point you have a quadratic model, binary quadratic model. And after this point, you want to choose which client you want to use to solve this particular problem. So in this example, I'm showing that I'm using Fixstars client. That's Fixstars Annealing engine. So let's suppose I have some token already. I'm registered, and I put some token here, and then timeout is set to one second. So this is in terms of milliseconds, so 1,000 milliseconds. And after defining the client, you give it to the solver class, which defines a solver in terms of the client that I defined just earlier. And using the solver, you get to solve the model. And after getting the result, I can just show the energy and the solution here. It turns out to be energy is the lowest energy because of the constraint is 1, and one of the solutions would be 0 and 1 in this particular case. So here is sort of like the basic flow of how you go about using Amplify SDK. So formulate problem, define client, and run the solver, and get the solution, and then do what you need to do using the solution. So this is the basic flow. Okay, so design goal of Amplify SDK. So first one is the formula manipulation. So what we need to do to go about the mathematical optimization problem is, so you need to prepare decision variables, and using those variables, you need to prepare objective function and constraints and so forth. And you need to go through a lot of manipulations in order to realize the problems that you are interested in. So Amplify SDK allows us to go through pretty elaborate manipulation of all these variables and objective function and constraints and so forth. Here's like only a few of the many examples, but if you are interested, please go through our documentation. But I'm just showing the gist of what can be done. So here you can define n by n array of binary variables in this particular case. So it's kind of like a matrix form, right? And using matrix like a representation here, which is same as NumPy here. And you can construct objective function in this manner, and then equal to function imposes constraint condition. So you give let's say 2 variables into equal to function, and that should equal to 1. So this means like addition of these 2 variables equals to 1 and so forth. We also have less equal, greater, and so forth, other like constraint functions and so forth. Okay, so through Amplify SDK, you can easily manipulate formula to realize what you need. And next one is a model conversion. So we need to deal with a lot of different machines, as I was showing earlier. So various machines, right? Through Amplify SDK, you can connect to a number of different machines. But what's to be noted here is each machine has different specifications. So variable types can be Ising, binary, integer, real, or polynomials can be linear, quadratic, or even higher order, right? And also some solver can handle a constraint, but some solver cannot handle constraints. It needs to be converted to Cubo and so forth. And also some types of constraints, if possible, it can be handled by some solver, maybe not by some solver, but okay. So we have equality, inequality, order of equations, special constraints, and so forth. And lastly, connections among variables. So here can be fully connected graph or specific types of graph. So after realizing a problem, you need to embed the problem into some physical graph. For example, if it's in the case of a D-wave system, you have a Chimera graph or a Pegasus graph. So you need to embed your problem into those physical graphs. So you need to go through all these details to tackle solving optimization problem using machines, right? So Amplify SDK simplifies all these complexities by going through different layers of the problem like this. So user's code is translated to input model first. And the input model can be whatever, or let's say it can be higher order. It doesn't have to be quadratic. But in a logical model layer, all the input model problems converted into a quadratic model by quadratization. And from this logical model, you need to also embed your problem into some physical system. So you need to, for example, the D-wave, Chimera, Pegasus, and so forth, right? So you need to transform the logical model into a physical model. And then after having the problem in the physical layer, this layer spits out some serialized data, and then that data can be handled by whatever the machines out there. And then the result comes back and then comes back in a backward direction to eventually come back to the user. So that's sort of like the design of Amplify SDK here. And then it takes care of all these differences of the solver pretty neatly. Here's a little bit more details about how the conversion is done. So in the input model, you, let's say, construct objective function and constraint. And constraint is quadratized. Objective function is quadratized. And in a logical model, you have a quadratic model. And the constraint condition can stay as it is. Or in a simple case, you convert the constraint into a penalty function, which is a quadratic model. And some solvers, some machines can handle constraint as it is. For example, Fixstars Annealing engine or Groby, this optimization solver. So it can handle constraint condition as it is. So for those systems, you can give the constraint condition as it is. So that's drawn by this blue arrow. Okay, so quadratic objective functions can be handled by, I guess, all the cases. However, for example, a D-Wave system handles only quadratic model. So the constraint condition needs to be converted to quadratic model. So in this kind of case, Amplify SDK knows that. So converts constraint conditions into quadratic model and then gives it to D-Wave system in this case. And then also SDK, Amplify SDK handles the embedding into a physical model. It's a D-Wave system example. So SDK has embedding driver for Chimera and Pegasus, and then takes care of all the graph embedding as well. And then after having data in the physical model, after that, the data is converted into the form that's communicated with the system out there to do the computation. Okay, and also algorithms is a third remark. In order to go through all these complications going about the layers, a lot of algorithms needed to be considered. For example, so only quadratic order functions can be handled. So if your original problem has higher order polynomial, like third order, fourth order, and so forth, it needs to be appropriately quadratized. And to do so, we have this algorithm called NTR-KZFT Ishikawa or substitution method. You can choose the method out of from the list, or if you don't choose, Amplify selects the best one automatically, and so forth. And also, penalty function generator for constraints. So in a simple case, the equality can be converted to quadratic function by just squaring the constraint. And inequality, it can be converted to equality by integer coding. And that can be also handled by this thing called the relaxation method. So it's not conversion to inequality, but the approximation method to handle inequality. So we have these algorithms to handle constraint conditions. Okay, so it's simple binary Ising conversion and also integer coding between unary, binary, and linear cases. And also handles the graph embedding, as I mentioned a little bit earlier. So King's graph, Chimera, and Pegasus graphs, and so forth. So Amplify SDK has a graph embedding driver to do this embedding of the problem into the graph, needed graph. Okay. So regarding to the versatility of Amplify SDK, and namely, I mean to say, can connect to various different systems. So again, showing the list of the clients that we can connect to through Amplify SDK. So Fixstars, Annealing Engine, DUA, Fujitsu, Toshiba, Hitachi, and Groby, IBM Qiskit, Kinesis, Kulax. So you can connect to these different clients. And connecting to all these different clients is pretty simple. So I'm demonstrating how simple it is in this slide. So first you construct quadratic model in this particular example. And after constructing the model, in this case, the left one is showing the example of connecting to D-Wave sampler clients using Advantage System 4.1. And the middle one is the Groby client. And the right one is the IBM Qiskit client. And after you define the client, you give the client class to the solver class. And using the solver class, you can solve the problem. And in all these different cases, different clients, you end up getting same form of solutions. So it's easy for us to analyze the results. Although if you use these systems in a bare form, of course, all these clients will give you different forms of answers, right? So in each cases, you have to analyze the results with different formats. But through Amplify, you end up getting answers in the same form. So it simplifies our analysis quite a bit. Okay, so in this slide, I'm showing that it's pretty easy to switch between different clients through Amplify. So, okay, being able to switch between different clients pretty easily, and also elaborately, you can tackle problems through Amplify SDK. I would like to demonstrate some benchmark a little bit. So here are the typical problems of benchmark that I want to show here. It's max cut for no constraint condition case, and the Sudoku here, number Sudoku. So this problem only comes with constraint condition. And the traveling salesman problem, and the quadratic assignment problem, and the capacitated vehicle routing problem. So these come with objective functions and constraint conditions. But yeah, sparse. But in terms of matrix, TSP is sparse and the QAP is dense. And okay, CVRP comes with inequality. So prepare this problem for because problems have different features. So using those problems, you can, let's say, perform some benchmark. So here, the first case, I'm showing that the comparison between Fixstars annealing engines with the two different GPU machines, V100 and A100. And on a problem of a traveling salesman problem with 124 variable. So in this particular case, you can see that a newer GPU A100 is outperforming the other one. So in this particular case, the number of variable is in such a way that you can put all the data into the shared memory of the newer A100. So it turns out to be faster. But when the problem is bigger and then it's traveling salesman with 299 variables, cities, in this case, you cannot put the data onto the memory on both cases anymore. So you don't really see the difference in the performance. So you can use Amplify to see this kind of differences. So a performance can depend on problem size, let's say, in this particular case. And comparison of different formulations. So what I mean by that is, okay, so I'm particularly looking at the CVRP problem using Groby client in this case. And so CVRP problem contains inequality. So inequality can be handled by a couple of different methods. So here I'm using binary method and relaxation method, and seeing how different the results turn out. So in this particular case, you see the orange one is doing much better job than the blue one. So binary method is the orange one, and the blue one is the relaxation method. So in this particular case, binary method is more appropriate than relaxation method. So you can understand something like this as well. Okay, so also this case, I'm showing the benchmark on the left one is a MaxCut with MaxCut K2000. So comparing Fixstars client and Groby client in this case. And in this particular case, Fixstars clients converges to lowest energy much quicker than Groby clients. But when it comes to CVRP problem, Groby seems to do a better job than Fixstars client. So the point is, like, depending on the problem, suitable client can be different. So using Fixstars Amplify SDK, you can switch client easily, so you can select appropriate clients for a given problem. Okay, so you can use Amplify SDK to see something like this. And lastly, I would like to show some case studies using Fixstars Amplify SDK and the Annealing engine. So one of the things that we worked on is the optimal assignment automation. So a digital transformation for logistics. So okay, so in a big warehouse. So I don't know if you can see this picture clearly, but it's a picture of a lot of people working nearby belt conveyor, carrying like some things. And then people have to sort the thing and then pack up the thing, and that those things packed up and then later shipped out, right? And in order to do that, you have to make some teams. In this particular case, 3 people, 1 person packs, and 2 people, one person sorts, and 2 people pack, this kind of team. But you have to make pretty good teams every day. And the manager, so this picture is kind of blurred, but meaning to show 2 people discussing in front of whiteboard. So it's roughly like 80 to 100 people. And then these folks have to consider good configuration, good teaming of all those people, a lot of workers every day. And then it's a lot of tasks. It takes about, we went to interview and then heard that it takes about 2 to 3 hours every day. So it's pretty overwhelming task. So we wanted to reduce this kind of burden using annealing technologies. So you can kind of imagine that, okay, you can express the problem. Okay, so we want to make optimal teams, basically, and then you can kind of imagine that cost functions that can be minimized in certain configurations of the teams. So for example, we want to make the team with people with similar schedules. And also, okay, so there are some groups that's in the company. So you want to pick the same people from the same group and so forth. And also we want to optimize the skills of the group, each team. So we want to optimize the skills, like a skill, skills of all the teams all together. So you can imagine that you can express all these things in terms of cost functions. So annealers can minimize this cost function under certain constraints, and then you can come up with the teams which minimizes the cost, right? So here it's kind of blurry, but we developed an application to handle this kind of assignment of the teams. And it's actually used in this warehouse. And then this 2 to 3 hour process every day for assignment was reduced to 15 minutes and so forth. And here it's since October, so it's not too long, but we hear that the mental burden was reduced and so forth. So we started seeing some results on, like, how annealing technology can be useful in some company setting. So this will be one instance to demonstrate that point. And another case that I would like to introduce is this simulation of phase separation structure of polymers. So here it's using Ising machine to simulate the phase separation structure of die block polymers. And so mapping basically phase field model to Cuba model. And okay, so in this particular case, we found the same tendency of the phase structures in comparison to the conventional model. And also it's we can obtain the result pretty fast. So in a conventional simulation, it was taking 100 minutes, but with this annealing method, only took about several seconds. So okay, it's a phase problem. So you have some order parameter, and you construct free energy using this order parameter. And in this particular case, you use some equation called Kahn-Hilliard equation, and you have some equation, right, to be minimized. And you go through appropriate discretization of this master equation. And okay, so you have energy to be minimized. And so once you have this energy described in terms of binary variables, what's left to do is to find the minimum of the energy using annealing. And you find the minimum of the energy, and then depending on the parameters, solution will exhibit different phases. So that's the results that we could also see in a result of the case with the Fixstars annealing engine. Okay, so in this particular case, we're making this point that it can be also useful in academic setting as well. And Fixstars annealing engine can be a useful tool to perform some of your academic calculations of interest. Okay, so this is the case study. And okay, pretty much this is the end of my talk. And then this is the summary of what I have discussed in terms of pictures. Okay, I would like to end the talk here. And then if you have questions, please. Thank you very much.
Good, thank you very much, Dr. Mizumatsu. Have a round of applause on behalf of all members of the audience. Good, thank you. So a lot of interesting things to discuss. If anybody has any questions, please either raise your hand or unmute yourself and speak up. Daniel Goldsmith has a question.
Yeah, thank you very much, Dr. Mizumatsu. That's a really interesting talk. Really appreciate that. But my question is, what
Yes.
do your customers typically use this tool for? Do they use it because it strikes me it'd be really good just to benchmark between different annealing models, maybe between a quantum one and simulated annealing. Is that what customers tend to use it for?
For example, this already has this particular example of warehouse has already customer. So this is one particular instance, and many other instances. But hold on. What should I mention? Formulation. Yeah, so I'm sorry. Yeah, not only this case, but not VGA, right? Many examples, but I'm sorry. I'm a
researchers or researchers.
In company setting. Yeah, but not the academic settings, right? Like in a company settings, right? Yeah. You're interested in like knowing the company setting examples, right?
Yeah, I mean, any examples? I was just curious as to what the tool. I mean, it seems a really powerful tool, to be able to compare all the different annealers all at once. And
right.
I was just curious. Is it used by academics to do academic studies of the different annealers?
Not only that. I'm sorry, like I'm kind of thrown off by like academic examples. So a number of academic examples, of course, but this is one company example, and then other company example would be
car,
like a car.
Car maker, car company.
Yeah.
Or
like optimization of VGA would be one of the examples, right? For example, AGV, like auto, how can I say, auto routing, auto auto, like automated vehicles, right? And then like some you have number of vehicles which are to be automized to do like certain tasks, and if you don't like take care of the routing properly, like some of the cars can collide and so forth, right? So you need to like find the optimal routing and so forth. So in this kind of setting, you can also use like optimization problem using Ising machine. So that can be one example. Yeah.
Okay, thank you very much. Thank you very much.
Yeah, I'm sorry. Like
Thank you.
I kind of thrown off by academic examples here. But
Thank you. No, that's really helpful. Like, really appreciate you answering the question. Thank you very much.
Yes.
Do we have further questions? A question from Professor Nishimori.
Okay, thank you very much for your very interesting talk.
Yes.
In your last example on page 25, you said that you achieved a similar result 100 times faster than the conventional method. I'm very impressed by the factor of 100. So what is the main reason of this acceleration? Is it because of the formulation of the problem, or is it the algorithm you used, or is it the hardware? What is the main factor that achieved this 100 times acceleration?
So I'm not author of this article, so kind of hard to answer the details here, but it can be okay. Number of variables is also reduced, right? In this particular, yeah, it can be combination of problem size and machine spec. I would think, and so in this particular case, I think problem size. Okay, problem size was reduced, but not too much to miss the feature of the problem, right? So in this case, it works out quite well to sort of like catch the feature of this particular problem. So yeah, but so when it comes to like what's sort of like essence, it can be hard to say. I mean, it can be combination of various things. Yeah. I'm sorry. Yeah, that's as much as I can answer at this point.
I at least understood that you reduced the number of variables in the sense of the possibility of values for each variable. So, well, that's one factor.
Right.
And another is the hardware. Or okay, I understand. I read that paper very carefully. Thank you.
Yeah. I suppose conventional phase field method should have more. It's finer in terms of you compare the picture. So yeah. Well, anyways, yes.
Any further questions? Well, maybe I could ask a question. Could you go to page 10? Oh no, there is a question. Sorry, I should allow other members of the audience to ask. So a question from Ryoji Miyazaki.
Thank you for great talk. And I'm very interested in the time required to formulate a problem. I'm very surprised with your SDK can formulate the problem very fast. And what I'd like to know is the scaling of the time required to formulate. I mean, how do the time increases with the problem size?
That's a hard.
That was my question.
For example, yeah, talking about this kind of character, right? How would you know? I guess, yeah, from formulation, maybe you would know that to some extent, but normally I would just run the benchmark to sort of capture this kind of trend. Yeah. Yes. I don't know if that answers your question in a expected way, but yes.
So you mean that we cannot determine some scaling in the algorithmic viewpoint?
I think algorithmically you should be able to analyze that to be able to tell to certain extent, right? I suppose, yeah. But you mean okay? So your question is like, does Amplify tell you like the sort of like insight on how it goes? Yeah, I would have to say, yeah, it can be case by case. Yeah, yeah. Analyze the problem analytically to find out to a certain extent and do the benchmark and confirm it. That's the sort of thing I would be doing. Yeah. Yes.
Okay, thank you. I got it. Thank you very much.
Yes.
Good. Thank you. Well, we're coming up to 10 o'clock in London, so I think we shall conclude there. Thank you very much once again to Dr. Mizumatsu for a very nice presentation. Thank you. Thank you for attending, everyone. The seminar series carries on next week, and we look forward to seeing you again at the next seminar next time. Thank you very much.
Thank you very much.
Bye, everyone. Thank you.
Thank you. Goodbye.
Bye.